This lesson's on nuclear reactions and specifically on fission and fusion, and here are the objectives. Remember, in an earlier lesson, we looked at the graph of binding energy per nucleon versus mass number, and we saw that there was a curve like this. Now remember, binding energy per nucleon is a measure of stability. Binding energy is the energy that is released when a nucleus is made up from its constituent nucleons. The more energy that's released, the more stable that nucleus is. So higher binding energy per nucleon is a more stable nucleus. And we saw that iron 56 was up here at the peak, the most stable. Now, that implies that if we can take a larger nuclei and split them into smaller nuclei going this way towards iron, and we call that fission, then we can make a more stable nucleus and thereby release energy. Similarly, if we take smaller nuclei and fuse them together, we call this fusion, getting a larger nucleus up here towards the peak, then again we can release energy. That energy released is the binding energy per nucleon difference between whatever we're starting with and whatever we're getting to. So there's two different ways of moving to nuclei with higher binding energy per nucleon depending on which side of the peak you're on here. Now also remember that mass energy is conserved in keeping with Einstein's famous equation, E is equal to mc squared. And we saw in an earlier lesson that one atomic mass unit, when converted into energy, releases 931.5 mega electron volts. And we did that by converting atomic mass units into kilograms, then putting it through this equation, getting out joules as energy, and then converting joules to mega electron volts. But if we use this, we can now skip that whole process because we've already done it. It's already been put through the E equals mc squared equation, so we can use this directly. So if we have an example equation like this, where we have A and B as our reactants reacting to make C and D as our products, the total mass and total energy on both sides of this equation have to balance. So if A and B are more massive, meaning if total mass decreases as we go from left to right, so there's more mass here, then that means that there must be more energy over here. Energy would be released, and that would be released as the kinetic energy of the products. So if we have a more massive set of reactants than products, then energy will be released, and that's going to be released as the kinetic energy of the products. And this is what we're going to see in both fission and fusion, and that's why energy is released, specifically because total mass is decreasing and mass and energy on both sides have to balance. In contrast, if the total mass were to increase, so let's say that instead the total mass is greater over here, then now we need to put energy in order to get the reaction to work. So we need to have more energy over here. That means that we need to fire A and B at each other at high velocity, giving them high kinetic energy in order to get this reaction to go. So in this case, if the total mass is increasing, then the reactants have to have kinetic energy equal to the missing mass. And that kinetic energy is showing up on the left side of the equation. It's not showing up on the right. On the right, it's showing up as the mass. So the reactants in this case must have kinetic energy equal to the missing mass. So these principles are true for all nuclear reactions. Let's take a look at an example, and then we'll get on to fission and fusion. So here we're given a reaction of helium and nitrogen making oxygen and hydrogen. We're asked to find the change in mass and then estimate the kinetic energy required by the reactants if this is going to happen. So you're given the masses here in atomic mass units. These two are on the left side. So let's make these positive, and these two are on the right side. We'll make these negative. And then I've calculated this ahead of time. If you add all these up, being mindful of your signs, you get negative 0.00128800 atomic mass units. In other words, there is more mass on the right-hand side of the equation. These are more massive. And so, as we said, this is an example of the second type of reaction that we looked at, one where we need to put energy in, that energy being in the kinetic energy of the reactants, in order to get that to show up as more mass on the right-hand side, again, by the principle of mass-energy equivalence. So how much energy do we need to put in? Well, we take this and we convert it using our conversion factor above. So we need to make up 0.0128 atomic mass units. one atomic mass unit is equal to 931.5 mega electron volts. We do that multiplication and we see that we need 1.19232 mega electron volts of energy. In other words, these two things have to be fired at each other with at least this much kinetic energy in order to create the mass that we see on the right-hand side. So that was an example where the mass of the products was greater, and to get that greater mass of the products, we had to fire the reactants at each other with high kinetic energy. That's what's happening in particle accelerators when they're being used to try and find new, more massive particles. But it's not useful if we want to release energy like we might in a nuclear reactor. So let's look at two processes that release energy. Fission and fusion, as I mentioned above, are processes of splitting apart nuclei or joining them together. And in both cases, the mass of the reactants is greater. So we've got more mass on the left side of the equation, so we must have more energy on the right-hand side of the equation. In other words, energy is being released. Another way of thinking about that is that the binding energy per nucleon, of the products is greater. The products are more stable. They are closer to the top of the graph that we looked at on the previous page, and their greater stability is because energy has been released in the process of making them. First, let's look at fission. Here we see a simulation from edumediasciences.com. We see a uranium-235 nucleus. This is the fuel in nuclear reactors, and we're going to fire a neutron at it. That neutron is going to destabilize the nucleus, and we're going to see it split into two smaller nuclei, a barium nucleus and a krypton nucleus, as well as 3 different neutrons. And now those neutrons themselves can, like the neutron we had at the start, go on and trigger new fission reactions, and so we can have a chain reaction. And this is what happens in nuclear reactors. Looking at that in equation form, we have our uranium-235 nucleus. We're going to fire a neutron at it. There's our neutron. The neutron has a mass number of 1 and an atomic number or proton number of 0, so let's fill those in. And then it creates this excited uranium nucleus. Notice that the atomic numbers and the mass numbers, the bottom and the top numbers, have to balance throughout. So that's our 236, 235 plus 1, and we stay here at 92, so we're still uranium. Then we saw that it split into barium and krypton. And if you look carefully at the numbers up here, at the mass numbers, you'll see that these are not quite the same as what were in the simulation, although the atomic numbers are, so it's still barium and krypton, just the neutrons have divided out slightly differently in this equation from the simulation. And then we also had 3 neutrons that went off in all directions. And those neutrons, like the neutron here at the start, can then go and hit other uranium nuclei and a chain reaction forms. And again, if we fill in the mass number and the atomic number here for each individual neutron, multiply by 3 and add across top and bottom, then we see that charge, the bottom number, balances, and nucleon number, the top number, balances as well, as is the case in all nuclear reactions. As mentioned, this is what's going on in nuclear power plants in a controlled fashion, and in a uncontrolled fashion in atomic bombs, where that energy is all released at once. That energy, again, is being released as the kinetic energy of the fission fragments, and that kinetic energy increases the internal energy of the surrounding parts of the power plant. For example, it heats water, that water is turned into steam, and that turns a turbine. So that's a broad overview of how a nuclear reactor works. And these neutrons can go on and fission other uranium nuclei, triggering a chain reaction, and controlling just how much of a chain reaction you have, how many of these neutrons fission more uranium nuclei, is a key part of controlling the power output of nuclear power plants. Too little of a chain reaction doesn't meet your power needs, while too much becomes dangerous. Let's look at nuclear fusion now with another simulation from Edumedia. We see that at a low temperature, the particles are not colliding with enough energy to overcome the electrostatic repulsion of the 2 protons. But if we increase the temperature, now they're moving much faster, and we can get them to fuse with an output of energy. This example showed 2 hydrogen nuclei fusing to form helium and another neutron with the release of energy. And this kind of reaction can occur when there's very high temperatures and high pressures, like in the center of stars. Again, that high temperature and pressure necessary to overcome the electrostatic repulsion between the protons that would keep the nuclei separate, and to bring them close enough together that the strong nuclear force can take effect. Here's an example of a different fusion reaction than the one shown in the simulation. We've got a hydrogen nucleus fusing with a neutron. Again, we'll put the mass and atomic numbers in there, forming a hydrogen nucleus with a neutron in it. This is deuterium, and a gamma ray. Again, a gamma ray or a photon is massless. There is more mass on this side of the reaction, as in both fusion and fission reactions, and that's coming out as energy on the right-hand side, as kinetic energy, and this energy of the photon. The reaction shown here and the one in the simulation are examples of the type of fusion reaction that's happening in the sun and in other stars, and building up elements of larger and larger atomic number. In fact, through processes like this, the sun is converting 4 million tons per second of mass into energy. That's tons, not kilograms. And that's how we get elements with larger and larger atomic mass number until we get to some that are actually only formed in supernovas. These processes require very high temperatures and higher pressures because of the need to overcome the electrostatic repulsion between the protons, keeping them apart. So that's an introduction to fission and fusion and an explanation as to why they release energy, namely that there's more mass on the left-hand side of the reaction than on the right, and so that missing mass shows up as released energy on the right-hand side.